Myself Muskan from BSc Chemistry Honors first year. Today I read a chapter of Inorganic Chemistry by Dr. S.K. Bansal, Dr. Ritu Dahiya, Dr. Rajesh Mehta, Dr. Ranjana Sharma. Chapter named Precipitation. In qualitative and quantitative analysis, formation of precipitation plays a very important role. For example, in qualitative analysis for cations, some of the cations are the first precipitated in each group and then precipitated as dissolved, and then each individual cations precipitated or tested. Similarly, most of the anions are identified by precipitation reaction. Moreover, inorganic qualitative analysis involving gravimetric experiment is based upon the complete precipitation of certain cations or anions. In this analysis, the substance is isolated from other subconstituents in the sample into a pure stable compound by precipitation, which can then be weighed. The amount of substance can be estimated from the weight of precipitation. Theory of precipitation. The precipitation is a process in which the soluble substance is converted into an insoluble substance with the help of reagent known as precipitating reagent. When the precipitating reagent is added to the given solution, the concentration of ions increase. When the ions product exceed the solubility product of that salt, precipitation take place. For example, the sulfate ions SO4 negative from a solution to be estimated. The sulfate ions SO4 negative can be precipitated as BaSO4 as we add precipitating agent BaCl2. With the addition of more BaCl2 that gives Ba2 positive ions, the ionic product goes on increasing, that is Ba2 positive SO4 negative. When the ionic product becomes more than the solubility product for BaSO4, the precipitation will occur. Optimum condition for precipitation. The favorable optimum condition for the precipitation process, that is, number 1. The process of precipitation is usually carried out in hot solution since solubility increases with rise in temperature. Number 2. The precipitation is carried out in dilute solution. Using dilute solution, the concentration of reagent is so controlled that the solubility product of the precipitated compound is only slightly exceeds with the addition of each increment of the experiment reagent. Number 3. The precipitating reagent is added slowly so that more time is allowed for precipitation, and thus build-up of large supersaturation is prevented. Number 4. After precipitation, the solution is cooled to room temperature to reduce solubility losses. The nature and rate of precipitation depends upon the particle size and particle growth. Number 5. As the drop of precipitating reagent comes in contact with the solution, there is relatively high concentration of reagent at the point of contact. So there is a high degree of local excess and high supersaturation. The process of precipitation is better occurs by slowly introducing the reagent throughout the entire solution. Number 6. Crystalline precipitates should be digested for longer period in steam bath. This process decreases the problem of co-precipitation. Number 7. To avoid co-precipitation of other impurities, thereby causing contamination of the precipitates, those should be dissolved in suitable solvent and then re-precipitated. Precipitation size of precipitates. The size of particle of precipitates has significant effect on the ease and completeness of separation of precipitate from the solution by filtration. The size of particles should be large because the large size particles are fully retained on the filter paper. The large sized precipitate are easy to filter and at a faster rate. If size of particle in finally divided form, they cause problem during filtration. Therefore, granulated particle carry down fewer contaminants during their formation as compared to finer particle. Factor affecting the particle size. The size of particle of precipitate depend upon the condition under which the process of precipitation occur. These conditions are: number 1, temperature at the time of formation of precipitation. Number 2, the rate at which reactant are mixed. If the rate of mixing of reagents are slow, they have enough time to come closer to each other. Number 3, concentration of reagents. Number 4, solubility of the precipitate at the time of precipitation. The solubility, it is the amount of substance dissolved in a known weight of solvent at a constant temperature, depend upon size of particle. When the size of particle smaller than 0.01 mm in diameter, the solubility increases largely with decrease in the size of particle. In this case, a supersaturated solution is formed in which the concentration of the solute is greater than the corresponding to the equilibrium concentration at the saturated state at the given temperature. Consequently, supersaturated state is unstable and may be brought to a state of equilibrium by the addition of a crystalline of salt, solute, or of some other solid substance. This is called seeding the solution. Seeding can be done by shaking, stirring, or scratching. According to P.P. von Weymann, supersaturation plays an important role in determining the particle size of precipitate. He introduced that the initial velocity of the precipitate is related to supersaturation as initial velocity of precipitation directly proportional to Q minus S upon S, where Q total concentration of substance, that is to precipitate. S is the equilibrium concentration is to saturated solution. Q minus S is the supersaturation at the moment when precipitation takes place, so that Q minus S upon S is the relative supersaturation. This relation is valid only when Q greater than S. It was studied by Weymann, the effect of supersaturation on the particle size. On the basis of the experimental investigation, he concluded that a marked decrease in size of particle occur with increase in relative supersaturation. For example, by rapidly mixing saturation solution of barium thiocyanate and magnesium sulfate are at relative supersaturation of 17, a relative supersaturation of 1, or a gelatinous precipitation of very small length of barium sulfate particle is formed. On the other hand, if very dilute solution of these two rearrangement are fixed, crystals of barium sulfate having 0.15 mm length of particle are observed. Explanation of dependence of particle size on relative supersaturation. Number 1. Nucleation, formation of nuclei. Number 2. Growth of the particle. Number 1. Nucleation, formation of nuclei. Whenever the process of precipitation occurs, a number of small particles are formed, that is, nuclei are formed. In a highly supersaturated solution, the rate of formation of nuclei is very large, while in low supersaturated solution, rate of formation of nuclei is less or even zero. Number 2. Growth of particles, nuclei. The formation of precipitate occurs by the initially formed nuclei. Once the nuclei are formed, the particles grow on nuclei and precipitation takes place. We have already discussed rate of formation of precipitation depend upon the degree of supersaturation. When reagent is added to the solution, it causes supersaturation. During the formation of nucleus, some minimum number of molecules or ions unite to form stable second phase. Its formation may also occur on solid contaminant in the solution called as homogeneous nucleation. It involves the arrangement of particles to form solid. The rate of homogeneous nucleation increase linearly with the increase in relative saturation, while the rate of growth of particle increase with increase in relative supersaturation. The dependence of rate of nucleation and particle growth on relative supersaturation is shown. Accordingly, if the degree of supersaturation increases, either the rate of nuclei formation increases rapidly or the rate of particle growth increases. If the supersaturation is kept at low level during the precipitation, the relatively less nuclei are formed and these grow to small number of large particles. If supersaturation is kept at high level, the rate of nucleation far exceeds the rate of precipitation, because of which the process of deposition of solid on the nuclei already present predominates. Therefore, it can be concluded that the condition of low supersaturation may favors the particle growth, while the condition of high supersaturation favors large fine particles. Factor affecting the solubility of precipitates. For accurate results, the precipitates must have low solubility, so there are many factors to create condition of low solubility of precipitation in the reaction medium. Number 1. Temperature. During precipitation, temperature plays an important role in qualitative and quantitative analysis. It is helpful to carrying out precipitation, filtration, and washing with hot solutions. In hot solution, the precipitates of large particle size are formed. They filtered rapidly and easy removal of impurities due to their enhanced solubilities. However, solubilities of precipitates increase with increase in temperature. Thus, hot solutions are used only in those cases where the increase in solubility of key precipitates is almost negligible with increase in temperature. In the other cases, the solution after the process of precipitation has to be cooled in the ice water bath before filtration. Number 2, common ion effect. Generally, common ion decrease the solubility of precipitate. For example, in the determination of Ag positive as AgCl, a chloride ion is added to the solution of silver. AgCl will contain 0.0015 gram per liter in aqueous solution. However, of a slight excess of Cl negative ion 0.01 molar is added during precipitation. Then the solubility of AgCl is reduced to 0.004%. Thus, the presence of even a small concentration of Cl negative ions reduces the solubility of AgCl. Number 3, adverse ion effect. While the solubility of precipitates decreases due to presence of common ion, it increases in the presence of ions which are not common with ions of the precipitate. That is adverse ion effect. For example, in the presence of 0.01 molar of KNO3 solution, the solubility of AgCl increases about 15% of its solubility in water. Number 4, pH of the solution. pH of the medium has a marked effect on the solubility of precipitate. Many precipitate are soluble in acidic medium. As a result, their rate of precipitation becomes slow. For example, calcium oxalate is insoluble in basic medium but in acidic medium. The oxalate ion tend to combine with hydrogen ion to form weak acid, that is oxalic acid. On the other hand, the precipitation of 8-hydroxyl quinoline with Al3 positive occur at pH 4. For example, for precipitation with Mg2 positive ion, higher pH value is required. Number 5, complex ion formation. Formation of complex with the cation or anion of the precipitate increases their solubility. For example, the solubility of AlOH thrice is extremely low in water at 298 Kelvin, but in the presence of fluoride ion, solubility of precipitate increase due to formation of complex of AlF6 negative. Similarly, solubility of CuI in water also increase in the presence of 0.001 molar Ki due to formation of complex such as Cui2 negative. Desirable properties of precipitates. In gravimetric analysis, there is complete precipitation of an element which is to be estimated. The precipitates should have the following properties. Number 1, purity. The precipitate should be completely free from impurities. The precipitate should be separated from the solution is the most pure form. Number 2, solubility. The solubility of precipitate should be small. Due to less solubility of precipitate, no appreciable loss occur when it is collected by filtration. Number 3, filterability. The size of particle of precipitate should be such that it can be readily separated from the solution by filtration. The size of particle of precipitation does not change during washing. The particle of the precipitate should be such size that they do not pass through the filter paper. Number 4, chemical composition. The precipitate should be convertible into pure substance of definite chemical composition. Number 5, non-hygroscopic nature. The precipitation should be non-hygroscopic, otherwise this precipitation may absorb moisture. It will become very difficult to weight it accurately. Number 6, non-reactive. The precipitation should be non-reactive. Number 7, fractional precipitation. The precipitating agent should be such that it precipitates only one element from the mixture of solution of many elements. Characteristic of precipitation. Number 1, homogeneous. Number 2, fairly large so that they do not pass through the filtering medium. Number 3, size of particle does not change on washing. Contamination of precipitate. Gravimetric precipitate is always contaminated with other ions present in solution. The nature of impurities depend largely upon the nature of precipitate substance present in the solution before and after the precipitation and the condition of precipitation. However, we have to reduce the level of contamination to a very low level so as to get accurate result. The contamination of the precipitation can occur by any one of the following process. Number 1, simultaneously precipitation. Number 2, co-precipitation. Number 3, post-precipitation. Number 1, simultaneous precipitation. If the solubility product of some compound also gets exceeds during the addition of precipitating reagent, the other substance simultaneously form a precipitation along with the desirable compound, then the desired precipitation will be contaminated with the second precipitation. For example, a mixture solution containing sodium chloride along with impurities of sodium bromide on addition silver nitrate will produce a precipitate of silver chloride contaminated with silver bromide precipitate. Number 2, co-precipitation. The separation of a solid form from a liquid which is it precipitated is never complete. Some of the soluble materials contaminate the precipitate. If they can't be removed by washing are said to be co-precipitated. Thus, the process by which soluble impurities become incorporated into precipitate during their formation is known as co-precipitation. For example, the addition of sulfuric acid to a solution containing a mixture of BaCl2 and FeCl3. We should accept only BaSO4 to be precipitated, but we obtain the precipitate of FeSO4 thrice also. The salt is soluble in water. However, this salt is partially precipitating with BaSO4. Co-precipitation may happen in many ways. A, solid solution co-precipitation. Certain substance when precipitated carrying with them as an integral part of the crystal other ions that would normally be soluble. Thus, barium chromate will co-precipitate with barium sulfate. Potassium ion co-precipitate with magnesium ammonium phosphate by replacing some ammonium ion. Chloride will co-precipitate with silver bromide by replacing bromide, and certain condition must be met. Number 1, the crystal structure of co-precipitated material must be same as the host crystal. Number 2, the ionic radius of co-precipitation ion must not more than 10% that of the replaced ions. Number 3, the co-precipitated ion must have not be very soluble, since less soluble salt co-precipitated by forming solid solution to a greater extent than the more soluble ions. Prevention. It can be achieved by converting the contaminating material into some other form. Thus, chromates as contaminants as barium sulfate can be prevented by converting the chromate to chromic ions. Number B, absorption co-precipitation. Imperfect or very small crystal that formed rapidly have very large surface area in relation to their mass. This large surface area exposed to the solution which attract ions of opposite charge, causing co-precipitation by absorption. Adsorption. Ions common to the precipitation are adsorbed most strongly. If BaSO4 is precipitated from a solution with an aqueous of barium ions, the barium ion will be strongly absorbed and will give a positive charge to the particle. The positive charge will draw negative ions from the solution, and if the crystal grow very rapidly, some of the adsorbed ions may be trapped inside the crystal. Similarly, if BaSO4 is precipitated from a solution containing an excess of sulfate ions into the sulfite ions, it will absorb strongly, giving the particle of precipitate a negative charge. Ba2 positive ions are adsorbed more strongly in BaSO4. See, occlusion co-precipitation. It is the trapping of fine impurities within crystal. This occurs when the crystal grows so rapidly that the ions is the precipitate do not have time to replace all the adsorbed impurities before the crystal grows around them. This produces distortion in the crystal and changes its composition. Less soluble ions are occluded most. Thus, nitrate is occluded on BaSO4 more strongly than chloride, since BaNO3 thrice 2 is less stable than BaCl2. Prevention. It can be reduced by adding finely divided solid, example broken glass, silica gel, and barium sulfate. The addition of aluminium ions, or by adding system a sulfur containing compound decrease the post precipitation of iron sulfide on copper sulfide. Moreover, by regulating acidity, the ions which are likely to be post precipitated should be protected by complex ion formation. Difference between co-precipitation and post-precipitation. The main point of difference between these are given below. Co-precipitation. Number 1. Magnitude of contamination is comparatively less. Post-precipitation. Number 1. Magnitude of contamination is comparatively large. Number 2. Co-precipitation. The magnitude of contamination decreases if the solution is agitated faster. Number 2. Post-precipitation. The magnitude of contamination increases when agitation is increased in speed. Number 3. Co-precipitation. Contamination decreases with time as the precipitation left in contact with the mother liquor. Number 3. Post-precipitation. The magnitude of contamination increases with the time as the precipitate is left in contact with the mother liquor. Treatment of the precipitation. Digestion of the precipitation. The purpose of digestion is to improve the filtrability and purity of precipitate. Most of the precipitate require digestive before filtration. The procedure for this sample heat of precipitation along with the solution from which these are obtained on a steam bath. These are obtained on a steam bath below its boiling point for 1 to 2 hours. Allowed to stand for some times. The heating can also be done on a water bath. Sometimes the beaker is kept at room temperature for 24 hours. Hence, the process of allowing the precipitate to stand in contact with its mother liquor for a reasonable period of time, usually 1 to 2 hours, either at room temperature or by warming at high temperature, is called digestion. Filtration and washing the precipitation. In this process, the precipitation are separated from the mother liquor by any one of the filtration media. During filtration, the precipitation is retained and collected on the filter paper, whereas mother liquor passes through it. Then, last traces of mother liquor is removed from the precipitation by washing the precipitates. The composition of washed solution will depend upon number 1 in the impurities to be removed, number 2 the chemical properties and solubility of the precipitate, and upon its tendency to undergo peptidation. Number 3 the influences of traces of wash liquid upon subsequent treatment of the precipitate before weighing. Characteristic of washed liquid. The washed liquid should have the following characteristic. Number 1 washed liquid should not form any volatile product with the precipitate. Number 2 it should not form insoluble product with the precipitate. Number 3 it should not have any dispersive action on the precipitate. Number 4 wash liquid should be easily volatile at temperature of drying of precipitate. Number 5 it should not contain an electrolyte which may interface with final determination in the filtrate. Number 6 precipitate should not dissolve in wash liquid but the impurities should dissolve readily. In general, water should not be used for washing the precipitate because it may cause partial peptidation and also cause some losses of precipitation due to slightly soluble of the solution in water. It can be prevented or minimized by adding number 1 by adding an electrolyte which gives common ion with the ions of the precipitate in distilled water. Example, to wash precipitate of calcium oxalate, a dilute solution of ammonia oxalate can be used. Number 2, if the precipitate have tendency to become colloidal, some other electrolytes may be used as washing liquid. The electrolyte should be volatile. It does not affect the precipitate. Example, the ppt of FeO ester can be washed by using ammonium nitrate solution. In some cases, washed liquid exhibit disability. It reduces the solubility of precipitate and it prevents peptidation. Dilute HNO3 is used for AgCl based upon the above discussion. Wash liquid may be divided in the following classes. Number 1, liquid which reduce the solubility of precipitate. The wash liquid may contain a common ion with the precipitate in moderate concentration of a compound. As a result, the precipitation become less soluble due to common ion effect. Number 2, liquid which prevent the precipitate from becoming colloidal. Gelatinous PPT becomes colloidal during washing. To prevent it, the wash solution should contain an electrolyte salt of an ammonium are widely used for this purpose. Example, for washing precipitation of FeO thrice dilute solution of E. NH4NO3 is used. Number 3, liquid which prevent the hydrolysis of salt of weak acid and base. Salt of weak acid and weak bases are slightly soluble in water and tend to hydrolyze to form a basic solution. Therefore, washing liquid must be basic. For example, the precipitating of MgNH4PO4 hydrolyzed to give HPO4 to negative and OH negative. Therefore, these precipitation must be washed with dilute ammonium solution. Precipitation during washing of the precipitation. Number 1, use minimum precautions. Number 1, use minimum amount of washing liquid to remove impurities. Number 2, washing should be done by using wash liquid into a number of small installments. Number 3, drain out the whole of the washed liquid before adding a fresh lot of washed liquid. Number 4, to check carefully that the filtrate not have the particle of precipitation? If so, take proper precaution for this. Added number 5, added pulp of filter paper to the precipitation before filtration for filtration of gelatinous precipitation. Example, AlOH whole thrice and FeOH whole thrice. These precipitation tend to clog the pores of the filter paper. Thank you.